Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 3 of a unit electromagnetic induction. So let's begin with today's class. In today's class we are going to discuss about the Lenz's law and conservation of energy. So first we will begin with the Lenz's law and then we will move further. So let's begin. What is Lenz's law? Lenz's law gives an easy way to determine the sign of the induced EMF. So basically the thing is that we have two laws. One was the Faraday's law. The task of the Faraday's law will be to give the magnitude of induced EMF and induced current, while the Lenz's law will provide us the direction of induced EMF. So with the help of with the help of Faraday's law and with the help of Lenz's law, we will understand the direction and magnitude. Direction by the Lenz and magnitude by the magnitude by the Faraday. Sorry. So Lenz's law states that the polarity of induced EMF is such that it tends to produce a current which opposes the change in the magnetic flux that is produced in it. In certain books, it has been written that it will oppose the one which will produce it. Oh, very good statement. It says that it will, that means induced current will oppose the one which will produce it. Always remember this. So Lenz's law says that it will oppose the one, or induced current will be flowing in such a way that it will oppose the one which will produce it. I hope this is clear. Yes. Now let's take an example and you will come to know what is going to be. So first let's discuss certain things and then we will switch to the numericals. So induced EMF E, that could be given as minus of n into d phi by dt if coil is having an n number of turns. Then we can say that E is equals to minus of n d phi by dt. This induced EMF is generated on account of the change in magnetic field, and we can say even this is magnetic and mechanical energy will be changed. So this law explains the direction of induced EMF as well as the direction of the induced current. Yes, this law is based on the law of conservation of energy. Always remember this. So let's discuss something about with related to Lenz's law and conservation of energy. Mathematically, Lenz's law is just the negative sign in Faraday's law. It is actually a consequences of conservation of energy. Therefore we can say that conservation of energy is contained in the Faraday's law as well. Now here in the law of electricity and magnetism, is there any explicit mention of energy or conservation of energy? All physicists believe that all laws of physics must satisfy the principle of conservation of energy. Yes, so what conservation energy is, that mechanical power put into the bar by the external agent is equal to the electrical power delivered to the resistor. So whatever the mechanical power I am going to provide to my circuit, that has to be used to deliver a power, and we always take an output from the resistor, that means the power delivered to the resistor. Energy is converted from mechanical to electrical, but it's just a change in the form of the energy, but the total energy should remain the same. And conservation of energy is obeyed by electromagnetic phenomenon as well. Yes, let's look certain quick questions. It says that the induced EMF is directed along the perimeter of the flux surface. The induced current in thus blank to the magnetic flux. Yes, it says the induced EMF is directed along the perimeter of the flux surface, so that in this situation induced current is thus perpendicular. It is the case when induced current is just the perpendicular to the magnetic flux. Let's look at the second question. it says that blank states that the polarity of induced EMF is such that it tends to produce a current which opposes change in the magnetic flux that is produced in it. Yes, this is the statement of the Lenz law. That Lenz law states that the polarity of induced EMF such that it tends to produce a current which will oppose the change in magnetic flux that is produced in it. Next, Lenz law. Lenz law is in accordance with the law of conservation of, yes, it's a law of conservation of energy. I hope this is clear. So this were all the theoretical part and theoretical sessions, theoretical information. Now let's look for the numericals and be ready with your pen and paper. Let's suppose the question is something like this. Here initially we are going to discuss about only and only the direction of induced electric current. So have your mind ready and let's work with me. Let's suppose a circular coil is given and magnetic field is given. This magnetic field is B is equals to B naught into T square. So the question to me is find out direction of induced, find out the direction of induced current. This is the question. So when this kind of question arises to me, my first checkpoint will be does it have change in flux? Does it have change in flux? Because if flux is not going to change, no EMF will induce, no EMF is induced, no current is induced, and everything has been vanished. So first question I should ask to my mind is, does it have change in flux? So what I understand is that when I discuss for the flux, it is B dot A, or I should write it as a B A cos theta. So what I should ask is whether B is changing. Yes, B is equals to B naught T square. It is changing with respect to time, and as it is changing with respect to time, B is changing, thus phi is changing, in turns EMF is changing. EMF will be there, and if EMF will be there, I am having the current. Yes, this would be the situation. So yes, it is having the change in flux. Now second situation is, if answer to this question is yes, go through the second question. That the second question will be, it will oppose the one which will produce it. This is the statement of Lenz law. It will oppose the one which will produce it. So the question should be, who is producing changing magnetic flux? So who is going to change the magnetic flux? This should be the second question. So if I look at this very carefully, then I understand that this was the situation. The magnetic field B is equals to B naught into T square. So the answer to this question would be increasing magnetic field changes the flux. So increasing magnetic field changes the flux. So now according to the Lenz law, again go through this, it will oppose the one which will produce it. Who is there to produce it? It's an increasing magnetic field which is producing it. So the direction of induced current will be such that it can reduce the inside magnetic field. Yes, a magnetic field is increasing, and magnetic field is inside the plane of the paper that you can see. Now, according to the Lenz's law, it will oppose the one which will produce this. Who is there to produce it? We should say it's an increasing magnetic field. So in which direction magnetic fields do exist, it is inside the plane of the paper. So what Lenz, according to the Lenz law, direction of induced current will be, it will flow in such direction so that it can decrease the magnetic field. Why to decrease? Because increasing magnetic field produces. So to decrease the magnetic field, we should say that to decrease the magnetic field, magnetic field should be produced outside the plane of the paper. Now, to produce the outside magnetic field, it is something like this. This is B is equals to B naught into T square. Yes. To produce the outside the magnetic field, according to the Fleming's right hand rule that we have learned in moving charges and magnetism, you need to produce a current in the anti-clockwise fashion. So if current is in anti-clockwise direction, then magnetic field will be outside the plane of the paper. So this is the direction of induced current. This will be the answer, that current will be in anti-clockwise direction. So always have this kind of question. First question should be, does it have change in flux? Because if there is no change in flux, there is nothing to worry about the direction, because no induced EMF will be there. If flux is not changing, no EMF will be induced, and if no EMF will be induced, no current will be induced, and that's so the question has been over at that point only. So first thing you must understand is, does it have change in flux? To answer this question, you must understand flux is equals to B dot A, which is equals to BA cos theta. So you must understand that any of the parameter is changing, whether B or whether A or whether theta. If yes, then you must remember the Lenz law, which says that it will oppose the one which will produce it. So your second question to your mind is, who is producing the changing magnetic flux? So in this case, the magnetic flux was changing because magnetic field was changing. How magnetic field was changing? With respect to time. Now as I will put a T, I understand that as soon as time passes, magnetic field will increases. So correct answer should be, increasing magnetic field will change the flux. So what I need to understand is, the direction of induced current will be such that it can reduce the inside magnetic field, because magnetic field here is within the plane. So to reduce the inside magnetic field, you need to produce a magnetic field which is outside the plane of the paper. How can you produce the outside the magnetic field? That by the current which is flowing in the anti-clockwise fashion. If it is done, yes, you have did it. I hope this is clear. You understand the complete sequence. Are you? Okay, great. let's focus on the question and you will be comfortable with this questions too. So the question is, find out direction of induced current in the below situation. So you need to find out the direction of induced current in the below situations. How will you do this? Let's have a look. First, see the diagram. That this was the direction of magnetic field, and this is given as B is equals to B naught by T, and this is the square coil is there. So let's think one by one. Yes, does it change magnetic flux? Yes, because magnetic field is changing, and as soon as time is going to increase, the magnetic field is decreasing. So what I understand is that my magnetic field is decreasing. If magnetic field is decreasing, my flux is decreasing. If flux is decreasing, that means EMF will be there. I'm talking about the induced EMF. If induced EMF is there, induced current would be there. Yes, so now my task would be to find out the direction of induced current. So let's begin with the second task. A second task says that it will oppose the one which will produce it. So who is producing it? I must say it is the change in magnetic field will produce it. Now I should say it is decreasing magnetic field. It is a decreasing magnetic field. It is decreasing magnetic field produces it. I hope you understand this. So as magnetic field is decreasing, and what I need to do, I need to oppose the one which will produce it. So as magnetic field is decreasing, I must try to increase it, and to increase the magnetic field, current should be in clockwise direction. Why in clockwise direction? Why? Because if you remember the moving charge and magnetism, at that we have a Biot-Savart law. It says that if current is flowing in the clockwise direction, then according to the palm rule you can prove this, or according to we have certain tricks, that if you assume this circular wire in it's a square wire in a circular frame, it's a virtual circular frame, and if current is flowing in the clockwise fashion, then the magnetic field will be inside. So thus you are going to support this. Yes, I hope this is clear. So in this coil current, this is the direction of induced current. This induced current will be in the clockwise direction. I hope this is clear. Is it clear? Is it? Do you understand this? Do you? Now let's do it. Next question. Find direction of induced current. So let's say that magnetic field, let's say it is something like this. It is something like this. Yes, the magnetic field is outside the plane of the paper. Everywhere magnetic field is there, and the coil is there. It is having radius r. Yes, and the magnetic field will be given as B is equals to B naught into T. So they want to find the direction of the induced current, how the induced current will flow in this. First, does it change in magnetic flux? Yes, magnetic field is changing. So if field is changing, yes, flux is changing. if flux is changing, EMF will be there. If EMF will be there, induced current will be there. Now what should be the direction of induced current? So the second is increasing magnetic field. Increasing magnetic field produces change in flux. Produces change in flux. Yes. So what I need to do is I need to decrease it. To decrease it, look at this. Magnetic field is outside the plane of the paper. It has been represented by dot. So if it has been represented by the dot, I must carry the current in such a way that it will produce a magnetic field inside the plane of the paper, and to flow it, I must understand that it should be the clockwise. This is I induced. I hope this is clear. Is it clear? Is it clear? Great. Let's work for the next question. Do it quickly. You are doing pretty good. Find direction of induced current. So the magnetic field is given something like this, and square frame is there, and it says magnetic field is 8 Tesla. Yes, this has been given. So first question, phi, it's a B A cos theta, but this is 8 multiplied by, let's suppose this is L, even this is L, this is 8 into L square. So it means no flux is changing. If flux is not changing, delta phi by delta t would be 0, or I should say EMF would be 0. So induced current would be 0. So if induced current is 0, no need to find out the direction of induced current. Yes, so always think from the first step to the last step. Always think that does it changing? If yes, then only think for the next questions. Otherwise, no need to think for this. I hope this is clear. Is it clear? Is it? Great. Now let's work for the next question. Find direction of induced current. Suppose the magnetic field is there in this region, and again this magnetic field is fixed, that is B is equals to, let's say, B naught Tesla. It is something like this. Yes, a square frame is there, which is moving with constant velocity v, and I want to find out the direction of induced current. So take your time, 20 seconds, 10 seconds, and let me know that what is to be done to find out the direction of induced current. So first question would be, does it have induced current? Does it have induced current? If yes, then we will think for the next question. If no, then that's it. Bye bye. Yes, what do you think? Yes, as you can see this frame, this rectangle, this square frame is moving inside the plate. So at one of the time situation would be that this has entered this much into the magnetic field. At other certain time this will be moving in this. Yes, so at one of the time it is moving like this, at one of the time it is moving like this, at one of the time it is moving like this, and now it is leaving, it is just the leaving the magnetic field, something like this. So let's give them a number, and please try to understand this. This was the first situation, this was the second situation, this is the third, fourth, fifth, sixth, seventh, eighth and ninth. So these are the different situations. So if you observe the situation from 1 to 2 and 2 to 3, you must understand this, that you must understand this, your area within a magnetic field, area that should be within a magnetic field is increasing. I hope you understand this, that area within a magnetic field is increasing, and if area is increasing, that means flux is increasing. If area is increasing, that is flux is increasing. If flux is increasing, flux is increasing, so what you need to do is, this is the magnetic field and this magnetic field is constant, but area is changing. As area is changing, what you need to do, you need to do something so that you can reduce the magnetic field. So current will be, current in first, second and third session is in the anti-clockwise direction. Why in anti-clockwise direction? Because due to this, magnetic field will be outside the plane of the paper. I hope this is clear. Is it clear? Now let's look at this situation, the situation 4, 5th and 6th. For situation 4, 5th and 6th, let's observe this very carefully. It's a 4 to 5 and 5 to 6. Have you seen this? Have you? Yes. If you observe this very carefully, then for the situation 4, the complete area was in magnetic field. For the situation 5, complete area is in magnetic field. For the situation 6, again the complete area is within a magnetic field. So what I understand is that 4, 5 and 6, flux is constant. And if flux is constant, delta phi by delta t would be 0. This will produce EMF is 0 and such induced current will be 0. So for the 4, 5 and 6, flux is constant. I'm not saying no flux is there. Flux is definitely there, but it is a constant flux, and if it is a constant flux, it is not going to produce an induced EMF, and if it is not going to produce induced EMF, that means that induced current would be 0. So great. Now in this situation 6, 7, 8 and 9, it is a transitory sessions. Yes, so let's understood it's a 7 to 8, 8 to 9. As you can see this, that by slowly it is moving outside, and at the 9th it is already completely outside. So from the 7 to 8 to 9, area is decreasing. When I say area is decreasing, do not understood that it is changing by its length. Area, when I say area, it's a area within a magnetic field. So area within a magnetic field is decreasing, and if area within a magnetic field is decreasing, it means flux is decreasing. If flux is decreasing, that means there is a change in flux, so EMF will be there, induced current will be there. So now for 6, 7, 8 or 7, 8, 9, EMF will be there. Now in which direction? As you understand that in this situation flux is decreasing, so what you are supposed to do is, you will oppose the one which will produce it. Who will produce it? It's a change in flux, or I should say decreasing flux will produce it. So what you are supposed to do is, you are just going to increase this flux. How to increase the flux? While providing a support to it. How to support it? By producing a current in the clockwise direction. It is something like this. I'm talking about 7, 8, 9. I hope this is clear. So in this situation 7, 8, 9, current will be in clockwise direction. Why in clockwise direction? Because clockwise direction will produce a magnetic field inside the plane of the paper. I hope this is clear. Yes, have you got this? Have you got this? Do you understand this completely? Do you understand this? Any doubts in this? Is there anything? Is there is there anything? No? Okay. So let me extend this question, that plot the graph for the flux versus time and EMF versus time for the previous question. So you need to plot this. You need to plot a graph for the flux versus time and EMF versus time for the previous question. So what I understand is that, look at this. In this situation, in this 1, 2, 3, in this situation, flux is increasing. In 4, 5, 6, flux is constant. And as soon as it is leaving, this flux is decreasing. So if this is the situation, how to plot this? It's a, let's say this is flux, this is time. Initially it is increasing something like this, then it is constant when this coil is moving within the magnetic field, and then it is decreasing. Yes, it is just the leaving phase of the coil. I hope this is clear. So this is flux versus time. Now let's plot it for the EMF versus time. It's an EMF versus time. So if I plot this, this is just the EMF versus time. These are the different time segments. Let's call it T1, T2, T3. This is 0. So the situation will be, if I work for the E is equals to minus of d phi by dt. Yes, this minus represents the direction of the lens law that we know. So as you can see this, from 0 to T1, what I need to do, I need to just plot the slope of this. And if I need to plot the slope of this, the slope is positive, this theta is positive, but here minus sign would be there, and as it is a minus sign, it would be in the negative. It is something like this. I hope this is clear. Let's call it as a minus of E. Now from T1 to T2, slope is 0. So as slope is 0, slope will provide me the EMF. So in this segment, EMF would be 0. It is on the 0 line. From T2 to T3, the theta would be greater than 0, which we call as an obtuse angle, and so that slope is negative. Here slope was positive, but slope is negative. I am having a one more negative sign is there. It's a negative, negative, positive, so this will give me the positive. So let's call it this as a plus of E. I hope this is clear. Yes, it will look like this. Does it clear? Does it? Are you sure? Are you sure? Do you have any doubts up till now? Do you have any doubts? Is there anything? Is there anything? No? Are you sure? Are you sure? Great. So this is the complete question. I hope you understand this. Do you? Do you understand this completely? Are you sure? Are you sure? So can it be done? Can it be done? Great. So ready for the next question? Ready? Let's have it. Let's suppose the magnetic field is something like this. And the coil is something like this. Yes, it is something like this. And the magnetic field, it's B is equals to B naught into T square. Let's give them a name. It's an A, B, C, D. So the question is find out direction of induced current. This is the question. Find out the direction of induced current. How will you do this? So according to the question, look at this. First, magnetic field is changing. B is equals to B naught into T square. And as magnetic field is changing and it is increasing, B is equals to B naught T square. So as soon as time will pass, this magnetic field will increase. And if magnetic field will increase, which will change the flux, it is basically increase the flux. And if it is going to increase the flux, which will create an induced EMF for me. And if it will create an induced EMF for me, what I understand is induced current will be definitely there. I hope this is clear. So now I need to understand what would be the direction. So let's understood that now in this situation we are having a two area vector, that this is the first area and this is the second area. We have two area. What you need to do is you need to always consider the bigger area, because it will create a greater amount of flux, because phi is equals to B dot A, and area would be higher, then the flux would be higher. So what you need to do is, as this is increasing magnetic field, when it is an increasing magnetic field, you need to flow the current in the anti-clockwise direction. Why anti-clockwise? Because it can produce a magnetic field in the outward plane. So this will be something like this. Now always do understand the one parameter of this, that always start it in negative x. Yes, that this is moving in anti-clockwise direction, and just go with the flow. Look at this. Yes, this is complete path. So from A to B, then from B to C, then from C to D, and from D to A. It was the path of complete, it is just the complete circular path. Yes, it's a circular path. I hope this is clear. Yes, so this is the direction of induced current. Always please keep in mind, I am even going to write this, that always find direction for bigger loop. While I say bigger loop, I must say it's a area wise bigger loop. Always find direction for bigger loop and then follow the flow of current. Always keep this in mind. I hope this is clear. Is it clear that you need to follow, always you need to follow the bigger loop? If that is to be followed, the things will be done very easily. I hope this is clear. Is it clear? Is it? Great. Let's look at this question. Let's suppose the situation is that this is magnetic field, and the magnetic field is inside the plane of the paper in this situation. Now a circular loop is there, and this has been connected like this. So the magnetic field is given as B is equals to B naught T. Now the question they will ask is find out direction of induced current. This is the requirement. Find out the direction of induced current. So what I need to ask is, again we have a step-by-step process, that magnetic field, it is increasing. If magnetic field is increasing, if field is increasing, that means flux is increasing. If flux is increasing, that means EMF, yes, it will be there. If EMF will be there, then current will be induced. So does it clear? Do you understand everything? Yes. So induced current will be there, that is for sure. Now what I need to do is that when two loops are there, as we have discussed, that always find direction for the bigger loop area wise. Yes. So what I need to do is, I need to, let's understood, this is first, this is second. First area is bigger than the second area, so it covers a larger amount of flux. And when it covers a larger amount of flux, what I understand is that I need to find out the direction for this, and then I will just follow the direction of the current. So for this, as it is increasing, what I need to do, as magnetic field is inside the plane of the paper, what I need to do is, I need to do the outside the plane of the paper. So this is direction of induced current. This is the direction of induced current. It is flowing in this, and then it will be moving like this. I hope this is clear. Is it clear? Is it clear? Do you have any doubts up till now? Do you have any doubts? Is there anything? Is there anything? Is there? No. Great. So look at this. If you understand this, that here, if you have make a rule according to your choice, that if bigger one is flowing, if current in bigger one is flowing in anti-clockwise direction, then current in smaller one in the clockwise, always do this thing, then this is completely wrong in this loop. That even in this it is an anti-clockwise direction, even in this it's an anti-clockwise direction. So in both the loops current is flowing in the same manner. I hope this is clear. So please do not make your rules, they will not going to work for sure. Please follow this rule only, that always find the direction for the bigger loop, and then you are going to follow the loop of the current, then flow of the current. I hope this is clear. So this is the direction of induced current. I hope this is clear. Is it clear? Great. So now shall I add something? Find out the magnitude of the induced EMF, because so many questions have been gone and we have not practiced it. So let's just do it. It's an E, that should be is equals to d phi by dt, that is equals to d by dt of b naught t multiplied by area. So this is equals to b naught into area. This is just the b naught into area. So this would be E is equals to b naught multiplied by area. This area, let's assume this as an R1, assume this as a radius of R2. So their area would be equals to pi into R1 square plus R2 square. I hope this is clear. This is the induced EMF. If they asked for the current, then I is equals to E by R. This could be written as, this is B naught multiplied by pi multiplied by R1 square plus R2 square divided by resistance. Resistance could be written as rho into L divided by cross sectional area. So this would be B naught into pi into R1 square plus R2 square divide by rho into length. The length will be, what will be the length? It's a 2 pi R1 plus 2 pi R2. It's a 2 pi R1 plus R2 divide by cross sectional area of this. What is the cross sectional area? It's I is equals to B naught into pi into R1 square plus R2 square multiplied by cross sectional area of this divide by rho into 2 pi into R1 plus R2. Yes, this much ampere of the current will flowing through it. I hope this is clear. And it is independent of time. It is independent of time. Even the EMF is independent of time. I hope this is clear. So, are you comfortable enough to do this? Are you? Are you comfortable with this? Are you sure? Shall we move to the next pattern of questions? Shall we? Shall we move to the next pattern of questions? Great. So let's work then. Let's suppose a ring is there, and this is a bar magnet. This is, let's say, south pole, this is north pole, and I'm going to release this from here. It's a free fall kind of motion. U is equals to 0 and it is going to move in this direction. So the question is find direction of induced current. Find direction of induced current in the given coil. How will you do this? How you are supposed to do is, so what you understand is, always remember the thumb rule. Always remember the thumb rule that use your right hand to make the north pole or south pole of magnet. If you curl your fingers in anti-clockwise direction, if you curl your finger in anti-clockwise direction, then thumb will form north pole, and opposite end will make south pole. Please do remember this thing, that we can use our right hand to make the north pole south pole of a magnet. So if we curl the fingers in anti-clockwise direction, then the thumb will represent, then the thumb will form the north pole. And if my thumb is forming the north pole for me, the other end will make a south pole for me. So the situation will be that it is something like this. This is south pole, this is north pole, and this is the loop. As it has been dropped from here, it is moving in this direction. So first thing is, does it change the magnetic flux? Yes. So the thing is, magnetic flux is going to change. Why? Because as soon as it is moving towards the coil, the magnetic field will increasing, because more and more number of magnetic field lines will link to this coil. I hope you understand this. Do you understand this? So as more and more number of lines is going to link with this coil, it will increase the magnetic flux. So flux is increased. As flux is increased, why flux is increased? Because south pole is moving towards this. So what you are supposed to do is, you are going to form a magnet which will have a south pole on the upper side and north pole on the downward side. Why? Because you want that this magnet should not approach me. Why? Because a flux is increased. I hope this is clear. I repeat it. Listen this, that south pole is moving towards the coil. What do you want? You want that you are going to oppose who is producing you. So what to oppose? You are going to oppose the motion of the south pole. How to oppose the motion of the south pole by repelling it. How to repel a magnet? By managing a same pole. Here south pole is moving in the downward direction, so what you are supposed to do is that you will form a south pole on the upper side of the link. And once you are going to form the south pole on the upper side of the link, then how will you do this? Then use your right hand. You want that north pole will be downward. So to provide the north pole in downward, thumb will represent the north pole. You need to rotate your fingers in the clockwise direction. This would be the direction of induced current. This would be the direction of induced current. Yes, does it clear? It is moving in the clockwise direction. I hope this is clear. Is it clear? One more thing. In this case, acceleration of magnet is less than g. Acceleration of magnet is less than g. Why? Because due to his repulsion, this A would be less than g. I hope this is clear. So now is it clear everything? Do you understand this completely? Do you understand this? Ready for one more question for practice? Yes, this will have a confident. Let's look at this. This is north pole, this is south pole. This is the coil, and it is moving in this direction. It has been, let's say, free fall. So what you're supposed to do is, first the question is find out direction of induced current. This is the requirement. Find out the direction of induced current. So what you need to do is that current will be induced. Why? Because north pole is moving towards the coil. What you need to do is you don't want that north pole will approach you. So you need to form a north pole on the upward direction and south pole on the downward direction. Yes. So to create a north pole on the upper side, of the link, this will be something like this. It is in this direction. I hope this is clear. And again, in this situation, A would be less than G. Yes, that's it. You did it. Great job. Do you understand this? Are you sure? Let me rewrite this. Are you sure? Ready for one more question? Let's have a look. Let's suppose a loop is there. And magnet is moving like this. It's a south pole, it's a north pole. Now it is moving in the downward direction. So first thing ask to your mind that does flux going to change? What was the answer of your mind? Mind says yes, it is going to change. Why it is going to change? Because magnet is moving downwards. It is moving away from the coil. If it is moving away from the coil, it means it is the number of magnetic field lines are decreasing through the link. And if number of magnetic field lines are decreasing, that means flux is decreasing. So what you are supposed to do, you want that this bar magnet should not move down. So how can you achieve this? By attracting it. How can you attract it? By creating a south pole on the downward side. If you are able to produce a south pole here and north pole here, then you will attract the bar magnet. If you can attract the bar magnet, that means you are not allowing this bar magnet to move down, and thus direction of induced current will be such that north pole can be formed in the upper side. So this will be the direction of north pole. This will be the direction of induced current. I'm sorry. I hope this is clear. Is it clear? Is it? So do you understand this? Does it clear? Is it? Is it clear? Is it clear? Is it clear? I hope you understand this. Yes? One more? One more question. Yes. We have a space over this. This is let's say south pole, this is north pole, and it is moving in downward direction. So what you are supposed to do is you want allow bar magnet to go. How can you achieve this? By producing a north pole on the downward side and south pole on the upward side. If you are about to do this, if you are about to achieve this, this will be the something like this. Yes, this north pole. Yes, absolutely. I hope this is clear. Is it clear? Is it clear? Are you sure? Are you sure? Are you? Great. So this is highly conceptual questions. These are very good conceptual questions. Yes. Ready for the next questions? Great. Tell me, do you have fun in this? I like this. Do you? Great. Let's work for the next question. Let's suppose it is something like this. A ring is there, and a bar magnet is there. Let's say this is south pole, this is north pole, and it is moving in this direction. So they say find direction of induced current. So what you are supposed to do, you will understand that this south pole is moving towards the coil. So what we need to do is we need to produce a bar magnet such that it can oppose the motion of this magnet. How to oppose it? That by producing a south pole on this side, north pole on this side. How to produce it? Is then it will be like this. Yes, how many of you understand this? If you have understand this, then you were totally wrong. You should not do this. Look at the gap. The thing is, current cannot flow. Please have look at the diagram very carefully. Current cannot flow through the coil, which is not closed loop. I hope you understand this. This current cannot flow if it is not forming the closed loop. So in this situation I would be 0, so no need to find out the direction. As well as one more thing, important aspect, it's an A would be equals to Z, because no one there who is going to oppose this. I hope this is clear. Is it clear? So now, do you understand the complete aspect of this situation? Do you understand this? Do you? Are you sure? Great. So let's just wind it up this session over here. This was the Lenz law, which will provide us the direction of induced current. So this two may complete each other. That Faraday's law will give me the direct magnitude, and Lenz law will give me the direction. Yes, please have a practice of magnitude as well as direction, because examiner is going to ask us the both. I hope this is clear. As many questions you are going to attempt, you would be quicker and more accurate one. And this is what required in this when we go through the magnetism. Basically magnetism is having a group which covers a moving charge and magnetism first, magnetism and matter second, electromagnetic induction third. And you can understand a little concern of alternating current and EM waves. This is basically the next segment of class 12. I hope this is clear. So please do this. As many questions you are doing, as much accurate you will be. Thank you. Have a good day. Take care.